So bottom line for the Hamming distance is nice, Hamming distance is easy, but it's quite coarse, quite naive. Yeah. So the problem again is that, well, if we have two sequences which have different length, we just align them as they are and just compute the differences, yeah, as they are. Yeah, and we introduce these artificial elements at the end, but sometimes it would be better, maybe for example those three guys here from the second sequence better match to those here than to those. Yeah, but they have to match to those because this is what the Hamming distance requires. Yeah, so maybe this would be a better alignment. So it would be better to somehow have the artificial element somewhere here for the second sequence, but we cannot do that for the Hamming distance because we just add these artificial elements at the end. And that brings us, as I said before, to the edit distance, because now the edit distance allows or even searches for the optimal alignment, whatever optimal means. We'll see that now. So the basic idea of the edit distance is, and that is, if you think about it, exactly the intuition what we just said, looking for the optimal alignment. Well, the basic idea is that the dissimilarity, the distance between two sequences, is now defined as the minimum number of some operations, so-called edit operations, that are required to transform one sequence into the other sequence. And the edit operations that we typically allow are insertions, so the insertion of an object or an element, the deletion of an element, and the substitution of an element for another element. Yeah? So here's an example, given the following two sequences Q and S again, so Tür, Schloss and Abschluss. That is the second example from here, that we had a Hamming distance for that of 10. Now if we look at the edit distance and the edit operations that we need in order to transform Q into S, what kind of edit operations do we need? Well, the minimum number of edit operations that we need are actually those 5 here. So we need 2 deletions. We need to delete the T and the L, and we need to substitute for the U, the A, and for the R, the B, and for the O, the U. Yeah, so those are the 5 edit operations that we need. All the others are matches. For those we don't need any edit operations. So we don't need to edit S here because we can match it for this to this S. We do not. We need not to edit the C here because we can match it to this one here, and so on and so on and so on. Yeah? So that would be the edit distance for those two sequences, much smaller than the Hamming distance, obviously. Yeah, and the mapping that we get with this minimum number of edit operations is the optimal alignment, the cost optimal alignment actually. Yeah, so the edit distance represents the costs of this optimal alignment of the two sequences here. Yeah, and that is much more flexible, obviously, because yeah, we can introduce these artificial elements here at different positions in the sequence. Yeah? Okay, so we can also formalize that. It's a little bit more tricky, but or at least looks a little bit more tricky, but it's not actually. So we have two sequences. Well, first of all, we need some more terminology. So we have a sequence Q consisting of n elements, and then we denote with start of Q or start Q the first n-1 elements, yeah, the prefix, and with last Q we just take the last element of Q. Yeah, so this is Q here consisting of n elements. The prefix containing the first n-1 elements is denoted by start Q, and the last element Qn here is denoted by last Q. Yeah? And because we need that now here for the definition. So now the definition of the edit distance, we need two sequences, Q and S. They can now have different length, as you see here. So the length of Q is n, the length of S is m. Yeah? And now we want to find the minimum number of edit operations that is required to transform Q into S. Well, of course, we have two very trivial cases, namely the first trivial case is that the second sequence is empty. So M is 0 in that case. In that case, S is empty. In that case, we need n deletions in order to transform Q of length n into an empty sequence S. So we need to delete all the n elements from Q in order to get the empty sequence of S. So that is the first trivial case. The second trivial case is the other way around. Q is empty, no elements, so n is 0, and S has some m elements. So in that case, in order to transform the empty sequence into a sequence of m elements, we obviously need m insertions. So we need to insert all the m elements here into Q in order to get S. So the costs will be m in that case. So this is very trivial. Those are actually the base cases, because this is a recursive function, obviously, or recursive definition. So those are the basic cases. Now the recursion cases. So we look for the alignment from the tail, from the end of the sequences, and we compare the two ending elements, so last Q and last S. If they are the same, if they are equal, then we know we have a good match, we have the perfect match, so we don't need to spend some edit operation. We don't, for matches, like here, for the matches, we don't have to count any operation. So if the last elements of the two sequences match, then we just have to look at the prefixes of Q and S and determine the edit operations, or the minimum number of edit operations required to transform the prefix of Q into the prefix of S. But we don't have to take care about the last elements of these two sequences, obviously. However, if that's not the case, well, then we at least have one edit operation to do for the last element. And the question now is, well, we can do that in three different ways. Well, we can use a substitution. So we can substitute the last element of Q into the last element of S. That would be one operation. And then we have to look for matching the prefix of Q into the prefix of S. Or we could stick with Q and eliminate S, so to say. So in that case, that would be an elimination of the last Q, of the last object of Q. So in that case, we have another first edit operation, of course, for the last element, and we have to look at how we can match Q, the entire Q, onto the prefix of S. And the other way around would be to match the prefix of Q on the entire sequence of S. So in all of those three cases, we take the first operation in order to not match the last Q to the last of S. But we can do that in three different ways: substitution, insertion, or deletion. In any way, we have one edit operation for this operation, and then we have to see if this one here has a lower cost than this one or this one here. So we need to compute the minimum of these three different options that we have in that case, and take the minimum of that. So we take the minimum of those three different things here. So a short remark: if no insertions or deletions occur, so if it's always like this one here or like this one here, then the edit distance is equivalent to the Hamming distance. So obviously this is a substitution. So the Hamming distance just counts the number of substitutions and matches, and does not allow for insertions or deletions. Yeah? So this here would be a deletion, and this would be here an insertion operation. Yeah? Okay, but that's, I think, quite clear.